All right. Okay, thanks. I'll try to be pretty brief. Basically, I just wanted to give a discussion that I think is a nice counterpoint to the discussion we've been having about infrared effects in most generally in single clock inflation. And this is I think, less subtle effect, but a pretty acute effect and pretty relevant in terms of making that between observables, of which we have not very many in cosmology, actually, when we look at our sky, and trying to figure out what the actual theory of inflation is. So the story I'm going to tell is it's a math story. It's for the most part a classical story. And I just want you to consider some very large volume, which is some time slice after any isocurvature modes have been converted into the adiabatic mode. So what's essential for this story is that it's not a single clock inflation. There really was some other light degree of freedom. Maybe it was a curvaton. Maybe it was some light field weakly coupled to the inflaton during inflation. But there really was isocurvature stuff. Zeta was not constant. All that stuff got converted to curvature. And this is just some time, let's say post-reheating. And consider a volume that's much bigger than what we actually see today. So, of course, at reheating, the Hubble patch was small, but let's consider a volume that's comparable to our volume today. And then there's everything else that was generated during inflation. And I want to also limit this to a volume so that I avoid issues. I mean, it's interesting to consider issues of eternal inflation, but I want to limit this to a volume that's just purely perturbative, so that if I look at the net size of fluctuations in this whole volume, it's all perturbative. And there's some set of stuff that lives inside here. I'm going to call these the short modes. Okay, short, I'm going to work in momentum space mostly. And this is the set of modes, which are the long modes. This is the big volume. This is the small volume. Okay, so I'm going to just out of habit, I usually write everything in terms of the Bardeen potential. So I'm going to write expressions for the fluctuations phi. And what I'm interested in is the case where we look at these fluctuations phi and we say that it's possible if, and this is the if that depends on it being not single clock inflation, if the set of modes k short are coupled to the modes k long, then basically three things happen. The simplest thing that happens is just that the statistical properties of this volume don't have to be the same as the mean statistical properties of this whole volume. Basically, if there are long wavelength modes in this background that aren't the mean, and the short wavelength modes care about that, then the statistics here are biased. So the first thing is just stats in VS, I'm going to say are not the mean stats in VL if VS is biased. The second thing that means is that even though almost exclusively people will give you a single prediction for what are the statistics in some multi-field inflation model, what it means really is that people need to be giving a probability distribution of things you could measure. So the inflation model predicts a distribution of statistics for the small volume. And the third thing that means, of course, is that anybody that only looks at one small volume has a distribution of stuff that small volume is consistent with. So stats in DS.
So in 2, you don't just mean the different trajectories that are available, I gather. You mean more than that, I think.
Yeah, I guess in terms of multi-field inflation, you could think of it as trajectories, but and so if all those trajectories really are converged in the sense of single clock inflation, there's no interesting effect. So you could think of it as.
But I thought you were talking about the isocurvature perturbations.
Yeah, so I guess if you thought of that as a map in that multi-field space, you could probably think of it as a.
But it's a quantum effect, not a classical.
Yeah, exactly. Yeah. Sorry. Yeah. So it's quantum at that level, right? At this level, we don't see that, but yeah, thanks.
Just so I understand.
Yeah. Please ask me, or anything about this basic picture, because of.
I mean, distribution of statistics is just a more complicated statistics.
Exactly. Yeah. I mean. Yeah. I think the thing that's interesting is I haven't been able to find, and this would be great if other people know, but statements in either condensed matter literature, math literature, about the generic effect of this mode. So generically, if you have generically non-Gaussian statistics in some volume, what does it look like in spatial subvolumes? It seems like a sort of a question that image processors or somebody should know, but I don't know the answer. So anyway, stats that you see in one volume are consistent with again, let me say a distribution, a spectrum with a distribution, or with a set, potentially large set of models. Inflation. So what I'm going to do is just write the way that you can treat this problem if you just write a statement about what the statistics in the large volume are and you try to do this subsampling, just to show you a little bit about what kinds of things can change. Because I think that it's certainly true that given a prescription for statistics in VL, you can work this out or you can do numerical realizations or something like that. That's not the question. What's interesting is what types of things can be confused, right? And if the only things that are happening correspond to sort of shifting parameters, in a sense, in this large volume thing, well, we don't really care because we fit those parameters all the time to get the spectrum index right or whatever. So I think what's interesting is this statement from the point of view of observational cosmology. What is it that we have to measure in order to be sure that we're not confused about what this, at least at any level we can never be precise about what the inflationary theory in this large volume is. Okay. All right, is everybody okay with the picture? Any other questions about this?
So I guess it's important that the VL is finite.
So what's going to be important is that there's something that cuts off the coupling between long and short modes at some scale. So we don't want to have infinitely UV modes coupled to infinitely IR modes, I guess. And here, if I just force myself to consider only a volume where things are perturbative, I'm sort of doing that by fiat. You could also do it if there's some light mass for the other spectral field, things like that. But yeah, if it's infinite, then I don't know.
Well, in this number 3, I mean, we already, just because of cosmic, just in a boring setting,
yes,
where everything is Gaussian and single field, we already don't quite know how to narrow down the model because of cosmic variance.
That's right. So this is a form of cosmic variance, but it's much more severe in the sense that the normal cosmic variance comes at large scales because we just don't have very many measurements of those modes. Here I'm saying if you have a scenario where your background matters and you have no access to that background, you have a cosmic variance potentially on all scales, and you can't. You have to make it, just like for the standard cosmic variance, you have to make an assumption about your large volume statistics to say what the size of that cosmic variance is. Does that make sense?
So there's some limit in which the standard cosmic variance is not important, but this one still is.
It's always important in the usual sense,
yeah.
But I would say this is a more serious problem because it affects all scales and because it can confuse qualitatively different types of models. But inherent in what I'm doing is the assumption that this is not a special scale. So I'm assuming that, if we shift this around, I'm not worried about effects at the level of the size of that. I'm always going to be sloppy with stuff right at the size of that patch. Nothing else? Okay. So the way that we can write this down is to just write an expression for phi, which is arbitrarily non-Gaussian. And I'm going to do that by writing sort of an arbitrary functional of the Gaussian field. And I'm just going to expand it. So there's some linear term, phi 1. So often this is just linear in the Gaussian field, but it can get corrections, so I'll keep it some capital phi 1. Then there's, let me just give a coefficient, FNL, times some term that's quadratic. So this is phi 2. Sorry. And let me just keep out to GNL, phi 3. So these things are just potentially non-local functionals of the Gaussian at order quadratic and cubic, etc. And the canonical example of this is, of course, the local one that you're probably familiar with. So this just says the non-Gaussian field, for example, might just be the Gaussian thing plus a term that's quadratic, corrected to keep this thing zero mean. So that's the normal local ansatz. And this is basically where you see that this effect can happen, because one way that people figured out to test for local type non-Gaussianity is to look at this thing called halo bias. And the halo bias story is essentially the story I'm going to tell you, but just for bias patches in our own universe. Okay, so then, often we write this thing in Fourier space. So let's write 5K. and all we have is some integral here. That guy. So the way I'm going to generalize this to this scenario up here is to just replace this simple FNL by some kernel in this integral. And that kernel is going to generate for me the bispectrum that I want, something else at fourth order, et cetera. And the way that it's nice, the reason it's nice to do that in momentum space is then I just split my momentum modes into long and short, and I just plug that into that ansatz and take the limit so I can find what the statistics look like in different subvolumes. So I'm going to generalize this to something which is phi of k, some FNL. I'm just going to make the P's explicit, so the way it goes is P1, P2. At every order, you should just subtract the variance of these things and then just have some kernel. Just depends on the momentum. And similarly at cubic order, so there's some long expression. Basically, there's 3 phi's here. Subtract the sum of all the phi's with the expectation values of the other 2 phi's and some other kernel. All right, and then I need delta functions to remove the extra. So it's always k minus the sum of the pi. Okay.
So don't we need two fields for adiabatic and isocurvature for expansion?
So that's what I'm saying. What I'm writing here is the end result of just it's like the Bardeen potential. I'm just writing the final adiabatic mode after I've done that conversion.
Right hand side, the expansion part field.
What's that?
In the right hand side.
Yeah.
Don't we need to include several different fields? Don't we just expand just?
So you could go backwards if you wanted to and write the different fields that contribute. This is not the inflaton, it's just the Gaussian. It's just a linear, I'm just expanding in the Gaussian field. So I really am writing after those, like after the curvaton has been converted.
Okay.
Right, so I'm working after all those conversions have taken place so that the only thing I have to write down is one field here. Yeah, I know it's confusing, sorry. I'm writing one field here, but this is the adiabatic curvature mode now, not the inflaton or anything.
Your only interest, there already are such effects, even in single scalar inflation. You're only interested in effects that are much, much bigger, that are not suppressed, right?
That's right. So basically, if you do these coordinate transformations, correct, to the coordinates that we see, you're going to have some corrections of projection effects here, and those are all small compared to the effects that I'm going to talk about. So if you're careful again with observational coordinates, which is this question about single clock inflation, you can do that here too, and you may generate some small correction term, but those things are all small. Any single clock stuff is small compared to what I'm saying. Is that okay?
Is that built in somehow into the parameterization, or does that just?
It's not. Here I'm just assuming that these are statistics that apply to the field as you observe it. So I'm assuming that you've done all of those corrections up ahead of time, and these are really the statistics of the observed field at some early time. These are just classical observed non-Gaussian field.
So those are just built into the size of the inverse FNL and GNL.
If you like, sure. That's right. So you've computed for me what these things are in the appropriate coordinates.
And the kernels.
Yes, that's right. Does that seem reasonable?
Sure.
Okay, so all I'm going to do is split up these modes into long and short modes. So I'm just going to write the Gaussian field as a sum of the long Fourier modes and the short Fourier modes. And there's always an e to the ikx that I'm sort of suppressing because whenever I'm looking at modes that are much larger than the size x of this volume, that thing's 1. So I'm not worrying about the e to the ikx because it's essentially 1 for my purposes. You can be more careful, but... and so I do this for the Gaussian field and same thing for the non-Gaussian field. And you just plug that in and proceed. And you can work out what the statistics of these guys are if you restrict to short wavelength modes. Is that okay?
With the short wavelength modes, you do want the e to the ikx?
Yeah, those guys have the e to the ikx. Sure. So yeah, what I'm going to do is I'm going to drop the e to the ikx for the long wavelength modes, just to keep, because I don't need it. I can keep it. But, yeah.
You're not trying to be totally general, I guess. I mean, because you could have shapes that couple long and short modes that are not captured by the single number FNL.
So all of that should be in the kernel. So often you can't really extract the scale independent FNL.
Good.
But this thing in here, maybe there's often, if it's scale dependent, there's not a good way to pull out FNL, but just to sort of,
Okay.
yeah.
Okay,
yeah.
so that's supposed to.
Yeah, so I'd like to be completely general by having this kernel completely general. And actually, if you keep the EDI-KX, you can, of course, work out stuff like the power asymmetry, because you can have little gradient modes across the horizon, but I'm not going to worry
You
about
can
that.
have all sorts of things that wash out against the top.
Yeah, exactly. But it's small. So. Okay, so basically my only job is to write these expressions where these k's are just restricted to the k shorts, and they have the normal statistics that we think, and to work out what the statistics of the corrections are. So what's the mean correction, of course, is 0, because the mean of the long wavelength modes is 0. And then because I've divided everything up as a Gaussian field, the only thing I have to compute here is the variance of all the corrections. So for example, if I just do this for the local ansatz, because that's much easier, if I take phi and restrict it to short modes, this is going to be the linear piece that I started with, plus a correction for when one of these guys is long wavelength. So for example, when I'm integrating over p, where p is much, much less than k, there's just going to be an integral here over those guys. So this is 1 FNL integral over the long wavelength mode. So this is p, much, much less than, let's put some cutoff k star for what divides long and short modes. And then, of course, I put in a scale invariant bispectrum, so I still have that for the short wavelength mode, so I still have the normal FNL term, where this is these modes are both subhorizon. So this is p greater than k star, k greater than k star, so this means k greater than k star. So this is the correction. So, of course, the mean of that correction is 0. If I take the mean of this thing, it's 0. And my only job is to compute the variance. So what's the variance? That's this integral d3p phi p squared. That's just going to be 2 copies of this integral, 2 copies of phi's. Take the power spectrum, I get a delta function. So this just ends up being d3p times the power spectrum of phi, integrated over modes that are basically in between k star and whatever you want to put for the infrared scale to cut it off at the moment. There's nothing that cuts it off.
So this is the same kind of procedure that Martin was describing yesterday, basically?
It's exactly the same type of procedure that you guys had written down, but what I want to pull out are the multi-field effects.
Yeah.
Yeah. And I mean, this procedure, this is something that observers do all the time, right? When they just ask what happens in my survey volume, which is not a large part of the universe. So nothing really surprising. What is this thing? So this is just integral, 1 over k if this is scale invariant. If it's not, you have a spectral index. And so this just gives you something like the amplitude of fluctuations times 1 minus the exponential of the number of e-folds, the extra e-folds, which is just the ratio of those. We put an e here for extra, times, we can check if I have the sign right, ns minus 1 over ns minus 1. So that if this is a blue tilt, so there's no power essentially on long wavelength modes, this thing dies off really fast. And if it's a red tilt, this changes sign, this is positive, and this is something that grows. So this is something that grows. And it depends on what the power spectrum is doing outside the horizon, which of course we have no idea what it's doing. So it's not a small effect. It's not a 10 to the minus 5 effect. It's an effect that depends on how much power you have out there.
Sorry.
Yeah.
E-folding between what and what?
It's number of extra e-folding. So it's the log, right? It's the ratio between the largest infrared mode in your problem and the mode where you cut it off, where it's the first mode that's outside your observable volume.
But let's see, in your observable volume, you would just measure the long distance mode, right?
So you can measure, you have to reset everything to the mean, in the sense that you measure your mean locally. Is that what you mean?
Yeah, I'm a little confused on, is that integral includes things that are outside the observable volume?
It's only things outside the observable volume. So in principle, once I've rescaled this local thing to be with respect to my local mean, I have no access to that observationally, right? It just is the background, which, does that make sense?
So if we take the single field limit, then such modes should cancel out as well.
That's right. That's right. So you can't see it here. You can see it if I write the formula for quasi-single field inflation, right? So basically, the way you can see it, though, in terms of the single at this level, is to take the equilateral bispectrum and put that here. And if you do that, what you get is a factor of k squared, p squared here. So that thing just dies away, right? So bispectra that are less coupled, they're more weakly coupled in the squeeze limit than the local type. There's extra factors of p in this integral, and it just dies away. It cares about 0.2 e folds or something like that.
So
right?
basically, it's about time variation of the garbage evaluation.
Yeah, the k squared effect, if you want. Yeah.
So,
Yeah.
sorry, just so I understand, as a semi-practical thing, is the idea partly that you could have a scenario where you don't see any FNL in the observable region, but it
Yeah.
contributed outside, and so you even thought it could be single field.
Yeah, exactly.
For
So
example.
exactly. So there's some. So I'll try to write a list of things that you might observe and be fooled by if you don't check other observables. But yeah, that's at this order. That's the thing that happens. Basically, you have a different amplitude of fluctuations. Okay, who cares? You rescaled your inflationary potential, but because you change your amplitude of fluctuations, what you pick out is the observable FNL, which usually we write the bispectrum in terms of the power spectra that we observe times the coefficient. Then you effectively change the observed value of FNL.
But that would still mean effectively it's single field inside the horizon.
Yeah. So the question is, what happens at the level of the bispectrum, I guess. Is that what you mean?
Could you answer Yuko's question again, or let me re-ask it? I wasn't quite sure I understood your answer to it. So she was saying that the effect must cut off if you took the limit of single field inflation. How do you see that explicitly?
Yeah, sorry. So there are two ways you can see it. One is that if you just put in the equilateral bispectrum, or a bispectrum that dies, with an x, as the equilateral does in the squeeze limit. So the squeeze limit, I don't know how much of this you want me to write on the board and how much is familiar to you, so let me know. But you basically just take that bispectrum as your kernel here, and what that does is give you a factor of p squared in this integral. No,
I'm getting a little confused. Does the model, what the model is, determines what N2 and N3 are?
Yeah, sorry. So what this thing does is you fix it so that it recovers for you the bispectrum. And if you do all these guys correctly, it's just the connected part of the bispectrum, the trispectrum, etc. So this is completely. Does that make sense? One way you can see it is to take the 3-point function of this non-Gaussian field, 3-point correlation, and see that the leading term comes from one factor of N2.
Okay, so the way I'm supposed to think of it is if I have a particular model, that will make a unique prediction for what those kernels N2 and N3 are. Is that right? And then the N2 and N3
That's
that you
right.
get for single scalar inflation would be ones that don't show a big effect.
That's right. Yeah, I mean, it's not quite unique. There's an interesting question about uniqueness. It's not quite unique, but that's the basic idea, that anything that has the right squeeze limit to be single clock inflation is just going to kill this integral. And you can actually see it nicely if you write the quasi-single field example too, because there the mass of the second field appears explicitly. So you can see that when that field is light, you recover this answer. When that field is heavy, the thing dies away. I can do that if you want.
Probably be too much of a...
Yeah. Maybe I'll try to get through the basic. Why is this important, and then we can do that.
So in this last formula, where is the assumption that you have multi-fields?
The assumption is that what I took here for the kernel is nothing, just constant FNL.
Okay.
And that bispectrum corresponds to local bispectrum.
Okay.
And if that's the real coupling, that's it. Thanks. Okay, so what are the interesting effects? Yeah, I don't know when time do you want me to be sure to stop by, or does it matter?
Well, how much time do you think you need?
I can try to be quite brief, and then people can ask me about details if you want. I mean.
That seems like a good approach because, well, things do expand due to discussion.
Okay,
so,
all right.
yeah.
All right, let me just try to list why you should care, what can happen. So let me make a list of input non-Gaussianity and local we say effects in biased subvolumes, because that's what's relevant for us. So the one that we just did is if we put in the local bispectrum, then that can shift the amplitude of fluctuations. And like I said, if we shift the amplitude of fluctuations, that shifts, this implies a shift in the observed FNL, just on its own. If you put in...
So if I think of a curvaton or something like that, that's just a shift in the local background wave of the curvaton or something like that, right?
Yeah, it's curvaton modes that are not the mean. So the realization of those fluctuations, the particular values of those fluctuations, which don't have to be the mean value, is what you're adding up here. In one particular observed volume, there's some constants. It's just the realization of the fluctuations. So I'm saying you're adding up the curvaton modes, but you don't want to do it statistically, right? Because if you do the average, you just get 0. If you do the mean, you just get 0.
So it's the local viv in our region.
So let's say you put a local type trispectrum, so a GNL type trispectrum, then you do this, and this gives a shift in FNL, but you also shift FNL in a way that depends on GNL times the integral over phi long, the sum over phi long, and if you shift the power spectrum by something that depends on FNL and GNL. And in fact, if you start with anything that goes like phi to the p, then you regenerate for yourself a term that's linear, a term that's quadratic, etc. All those terms with appropriate FNL, GNL, etc. And this can look, if it's sufficiently biased, this can be weakly Gaussian, weakly non-Gaussian.
Here, are you assuming you're measuring the long mode or not?
No, I'm assuming you can't measure
So when
it.
you say you shift A0, so
Yeah.
I mean we measure some A0
That's
and
right.
we don't know whether shift is.
That's right,
relative.
exactly.
Okay.
So that's the sense in which I'm saying we measure what we measure, and that stuff can be consistent with a wide range of possible,
But aren't we supposed to divide the sky into shorter regions and longer regions and then check the...
Exactly. So that's the only way out of this, right? That's the only way we can check if we have to worry about this. And so I'll talk about that at the end.
Okay.
Yeah, exactly. Yeah, I want to write these things because it's a little bit surprising sometimes what you can get locally from what you put in, right? So something that looks very non-Gaussian can look weakly non-Gaussian in biased volumes.
Sorry, what does phi to the p mean?
Sorry, instead of writing, I'm sorry, yes, I'm assuming you know something about the local ansatz, right? So a really simple thing that I could do here is just write this thing, this is the linear field, this is FNL phi squared, this is GNL phi cubed, ... So I'm saying if I just write any one of these terms,
I see.
pick any one, that's what happens. So something maybe more interesting is if I put in some other types of trispectra, and now this is a little bit like fishing for what trispectra are interesting, but let me just call them troublesome trispectrum number 1. Troublesome trispectrum number 1 will shift A naught, and it will generate B equilateral. And troublesome trispectrum number 2 will not shift A naught, it will just generate B equilateral. So that's a scenario where you could measure, if the only thing you did is you measured the shape of the bispectrum and nothing else, you could say, it's equilateral shape, so we must have single clock inflation. But unless you check some of these other ways of checking if you're being fooled by this cosmic variance, you don't know that actually. And this is, mathematically this is kind of obvious, right? If I measure the shape of some lower order correlation function, it doesn't tell me anything about the shape of the higher order correlation functions. So, measuring this shape alone, I can't assume anything about what the shapes of the higher order things are, whether they're consistent with single clock or not. So the only ways out of this, right, that you can see if this effect is relevant is to try to do some measurement which divides our sky that we have up into small regions and see if you have this type of effect. So the way that you can check, let me just make another list and then I'll stop and we can just discuss it. Oh, this is, is this relevant? Oh, I forgot to say there's one other good one, which is that if I put in if I put in FNL of K, then I also shift NS. Because basically different modes inside the horizon couple with different strength to the single long wavelength background, so that gives me a scale-dependent shift to the power spectrum.
So, excuse me, can I have, for example, FNL local be 0 if you put some inputs? There?
Sure.
So you would think that you are in single field inflation, but you're in fact not.
Good. So if I insist that region is perturbative, the smallest that I can get if I allow sort of arbitrarily large non-Gaussian in a small volume, the smallest I can get is FNL of order 1 in a small patch. So it's weakly non-Gaussian, but I can't get it to go away unless I assume that I allow myself non-perturbative levels of fluctuations, which you might say, well, why not? Why can't I do that? And go to some part of the eternally inflating landscape. But if you insist that it's perturbative, you have that weak limit. Thanks.
Is there some theorem that says that each of these choices here corresponds to a real model?
So there's not a theorem. I guess we know examples if you believe that things like curvaton make sense. And people have done also sort of other multi-field models where the two fields don't have exactly the same potential or something like that, which generates for you a scale-dependent FNL. So I would say, this stuff, of course, makes people believe that there are models that are good, very good approximations to that. This no one would write down, but I'm telling you that observationally you can't tell the difference. This, no one has written down a model that generates these things, but I think given the set of stuff like curvaton and quasi-single field that we know that generates this range of local type couplings, I'd be surprised if this is forbidden for some reason.
Is there some way to reconstruct the model by knowing this, by knowing those kernel functions in 2 and in 3?
I'm doing a prescription for the trispectrum. So if you can find a model that has that trispectrum, which you can sort of map to some interaction, you can probably do it in a relatively straightforward way. At least for some things. But I guess, yeah. Also, what I'm using here are sort of idealized versions of these, which are scale invariant and factorizable and things like that, which in most models, what you get isn't exactly that. It's approximately that. But okay, so let me just make my list here, and then we can discuss. Is this relevant? So, the first thing you do is obviously is you check for local type squeezed limit in the bispectrum. And you have to check at least down to order 1. I'd say what Planck has done isn't enough to confirm that this effect isn't there. And you have to check for that at all scales, essentially, that you care about. Some things you can do that are different. You can check for things like the non-Gaussian halo bias. So basically, halos aren't average regions of the density field. They form an overdense region, so they they are biased. And then they pick up this effect with a pretty strong scale dependence because this is the density field, and that's in the gravitational potential. And really, this halo bias picks up any contribution that shifts the power spectrum. So it picks up squeeze limits of lots of higher order correlation functions. So you could, in fact, if you're in some scenario like this, see an equilateral type bispectrum but have a contribution to the non-local halo, to the non-Gaussian halo bias, which is kind of interesting. The other thing you can just do, sort of the analog of this, is you can check if we have the ability to map out the density field, weak lensing, whatever, you can check for correlations between, for example, the matter power spectrum and background density. But then that all gets you somewhere here.
What is the background density?
Sorry, I mean if we can actually map out, through weak lensing or something, all the dark matter fluctuations. So you can see what the background density fluctuation is over your survey volume, for example, and then you measure the power spectrum in that survey volume.
So a longer mode.
Sorry. Yeah. Background, this means the sum of the P short in our volume, or the P long. And then I think the problem with these things is that you have to then go so you can again check the shape of the trispectrum shape, right? And that's already getting much harder, just statistically. And you can also check, similarly to this idea, you can check for position dependent. So again, correlation between the bispectrum shape and this sum over P log, the background density. So that's all good. The issue I have with this, I guess, is that it looks like there's enough space mathematically, so I'm not asking necessarily what inflation model does this, but for me to write down something at the next order, which, induces for me some equilateral bispectrum and nothing else at all. And it becomes harder and harder to actually measure those correlation functions at each order because they're small and you need lots of statistics to do that. And so it's not clear how far we can go, and it's also hard to do these kind of things because you need good statistics in many subvolumes, and you have to be able to map out along, what's your background for that. So it's not clear how far we can go with this program. And then I wonder, given how big of an inflationary landscape we could have, how much do I worry about this? And in something like quasi-single field inflation, where I'm on the limit at some coupling, does that change, when I change the shape of the bispectrum, does that change how I'm interpreting the particle physics that's there? Just because I don't have the ability to measure all those correlation functions. Okay, so that's where I'll stop. We can discuss it.
Good, so we've got time for questions, discussion, etc.
Do you have some picture you want to show us?
I can show you pictures if you want to see like probability distributions for some models and stuff like that, but it's just if you want to see them, it's not.
So what's the relation between the number of data points you would need and the ability to resolve different sorts of...
Yeah, that's a really good question. So some people have worked out, some of this stuff has been worked out. So people have said, in practice, with future large-scale structure surveys, can we measure the halo bias in order to get FNL of order 1 and things like that? And this is still futuristic because we have to understand very well how to actually do that with the luminous objects that we see. We don't see the dark matter halos directly. There are also some recent papers working out this idea that you look for position-dependent power spectra. And there's some very limited forecasts about that, because then again, you also have the gravitational effect that you have to be able to calculate that gives you this already, because it gives you some coupling between modes. And this one we're trying to give some estimate for now, this position-dependent bispectrum. So I can't give you a precise formula yet about all of this that's actually realistic. Sometimes it's just mode counting. You just want good enough signal to noise, right, in each of these things. You want a small enough volume, but not so small that you don't have a big enough signal to do this. So, sorry, I can't give you a formula, but it's just mode counting for signal to noise. So.
How much would it be changed if we could begin to resolve polarization? In the same thing?
So if I was just talking about the scalar fluctuations, then... So then, just like Planck's data release gave us some factor of 2 increase once they added polarization to density. It's another little bit of a factor, but probably really it's large scale structure ultimately, if we can make use of all those modes, or 21 centimeter or something like that, where there are just more modes that we have access to that would give us better statistics for this.
Okay, one final question. In the old days, a lot of people thought that one thing that we needed to do to tell whether it was single scalar inflation, or at least check, would be to check the single scalar consistency relation. Suppose we did that, how likely is it that would be giving us a false positive?
But here, you're asking about something to do with the tensors relative to
That's right.
Yeah, so basically, there's this shift, but that you can put that into the consistency relation, that's fine. The tensors are more interesting, I guess, because if the tensors are also subject to this effect, then that's interesting. But probably tensors are more robust, and because you just have less couplings that you can put in, even when you include couplings to other fields. And so I don't know if you can say absolutely that tensors are immune to this type of coupling or not. But they maybe are slightly more protected. Is that fair or not? You're shaking your head no. Okay.
Sounds reasonable.
So just so I understand, it still seems like if we use the data to exclude a lot of stuff, which we can do, which is perhaps the most powerful use of it right now.
Yeah.
How much does this obstruct that? It sounded to me, correct me if I'm wrong, but it sounded like you were saying that we could observe nothing, and yet it's because of some cancellation between something that was there and some higher order thing that fed back and canceled the thing that the earlier effect. But that sounds very fine-tuned to happen. Is that fair?
That's what I'm not sure is fair or not, because the questions of what is fine-tuned, first, I don't understand the entire, once I write down the entire hierarchy of correlation functions, what's fine-tuned or not, and the only example that's really easy is this one, where it looks stupid to write down an arbitrary phi to the n and nothing else, but in sufficiently biased subvolumes, and almost all volumes are biased to some extent, you regenerate something that looks local. So you have to tell me how unlikely the set of models are that have those types of couplings of this more troubles. I'm sorry.
You're saying it would generate something local, right?
So this would generate something local. So I guess the question is, in this case, how likely is it that I have this class of stuff that can give me something that looks equilateral at cubic order?
No, what I'm trying to say is if to see is zero, the constraints just keep getting tighter.
Oh, yeah. Sorry. Yeah, so if we keep seeing nothing, I agree, we should just probably forget about this. If we see nothing to all orders that we can
measure. Even though
measure,
it's logically possible,
yes.
as you said, that there could have been a cancellation.
Yeah. Then,
that would be ridiculous.
yeah, but so what's great about that is if we see really nothing, then the scalar is really protected degree of freedom, and that's really interesting also.
Yeah, I mean, it's a very powerful, it's very powerful used that way, I think.
Seeing nothing.
The data, yeah.
Yeah, absolutely, yeah. I guess what I worry is if we see something at the cubic order that tells us things are coupled,
sure.
Then we're in this nightmare. I mean, if Planck had seen something, God, I'm really glad Planck didn't, because we would have no idea what was going on.
What do you think
In some sense, if it was a large local time.
What do you think about the 3 sigma multi-frequency oscillations plus equilateral? You call that nothing?
Yeah, I don't know what that means exactly.
So again, about the single scalar consistency relation, suppose I make the assumption that nothing happened, that this doesn't contaminate tensors at all. It still would contaminate R, because R is the ratio of the tensor power spectrum to the scalar.
But in a way that's consistent with inflation. So you would just say it's some other ratio than maybe the mean ratio, but I don't think it really... Right, I mean, all this stuff just tells you shift the parameters of if you're just making a model for R.
Change the relation for R?
Yeah, but in a way you can't observe, I guess, right? Because it changes the power.
How do I see that?
Just what you just said, that if I have this type of shift to the power spectrum, then, and the tensors are unaffected, let's say, then the ratio of scalar to tensor is changed from what the mean is, the mean prediction in the whole large volume, but in a way that's consistent with inflation. So that value is different, just like the value of FNL is different, but you have no idea that happened. So it doesn't show you that there's something. Sorry, your friend also, did I say something confusing?
I'm just, so I'm having a little bit of trouble focusing on how this stuff depends on the model, but suppose that there really is curvaton perturbation, and it changes the single field results so that R is no longer, 16 epsilon or something, but the tensors are not affected by that, so that the tensor power, the tensor spectral index is still.
So this is 16 epsilon with some less than 1 factor, right? Some cosine here, right? So let's just call it number less than 1 in the multi-field scenario, and this is just P. It's over P scalar. So all I'm saying is that observably, we want the observed value of this. This could go up or down. This could go up or down. But that's just like shifting this number or this number, and that's still consistent with inflation, right? I'm not going to, because I don't know. Sorry.
But the relation between that and n sub t is not necessarily consistent with it. Yeah.
It's some other potential, though. Right. I could write some other potential that would, some other multi-field event.
There's a relation that's independent of the potential. If you have the tensor tilt and the scalar tilt and the ratio of amplitudes, then there's a relation for any potential.
But I'm saying, for a single theory, but I'm saying if that gets shifted, you would just interpret that as some other potential, or some other theory. Some other theory. Sorry, some other
field in it, like a curvature.
Not if you mention the tensor field.
Sorry.
But that's of course different.
Do you have the sound speed in there?
Could I put the sound speed in there? Do you want the sound speed in this? Is that what you're...
Well, I thought they were counting parameters, and that should be in there if you're trying to do single field.
So I'm confused. Maybe there's something obvious I'm not seeing, but isn't there such a relation that's just exactly, up to second order effects true in single scalar inflation that would then not be true if I had a multiple field inflation.
Okay, sure. Sure.
Yeah, because my issue is how much could this contaminate it so that if it was multiple field inflation, would get a false positive for the single scalar consistency.
Sorry, I guess my impression is that all of the contaminations hang together in the sense that the corrections go into the power spectrum
be single field.
How can that be? You're assuming that nothing happens to the tensor spectral index.
By hang together, I just
so
mean that.
N sub t is unchanged.
Right. So maybe I'm saying something wrong. But by hang together, I just mean that the values change, but in a way that you can interpret as a change to the inflationary model. I think that's true.
To the multi-field.
Right, to the multi-field inflationary model. So you would measure some. Right, because the whole thing assumes that I have some effect for multi-field.
So you would, even in spite of this contamination, you would still be able to verify the single scalar consistency relation or refute it. Is that what you're saying?
There would be consistency at the level of that relationship, and you detecting a type of non-Gaussianity that has to come from multi-field inflation. So the extent to which you're able to do that, which is FNL order 1, should be consistent with your ability to check the single field expressions versus multi-field expressions for stuff like this, I think. But maybe I'm.
I guess it could be for some choices of it too. I never understood how those things do it.
It sounds like you should have some more dialogue about that.
But for the model builders,
yeah, go ahead.
So your message for model builders was if someone makes a model and they give you, non-Gaussianity, and they give you more than the minimal 60 folds of inflation, then they have to also give you the probability distribution for what they should be seeing in the different volumes before they can make the standard statement that you're going to see this in the sky.
That's right. So your model of multi-field inflation with some FNL local or GNL thing is, there's some consistent with our universe, provided our universe is a 1 sigma fluctuation from the mean, so yeah, there's some PDF of what we should see. So if Planck gives you a value of FNO local, that's not your model and only your model. That's a wide variety of models.
Anything else? Okay. Well, thanks again.